Hey, Advanced Chem. Hope everything's going great. This is lesson number 9, the penultimate mandatory lesson for you. Again, like I said, hope everything's going great so far. I've been doing a lot of housework, been doing a lot of yard work. I'm getting a little antsy, you could say. I just want to see people. I just want to go places. I want to go out to eat somewhere. Not that I don't enjoy cooking at home. I like cooking at home. I think it's fun. It's an enjoyable experience. It's just when you do it so often, it's like, okay, you need a little break. It's kind of how I feel about not being in the classroom. Big part of me that's not the same is, or at least in my life, is that one of my biggest hobbies is teaching science. So that's a big part of me that's just cut off right now. And no, teaching in front of a computer is not the same. It's not even close to being the same. I can try to make it the same, but it's not even close. I like having the space, all the board space, the lab materials, doing demos, doing the labs, talking to each of you. It makes my day, and I guess in life in general, you really don't know what you're missing in life, or don't know how good something is until it's gone. It's crazy how that works. And the same thing for school. I know a lot of people say, school is terrible and you don't want to go to school, you hate going to school, but all of a sudden that's cut off and you have to learn online. And it's different. It's super different. You're like, oh, I just wish we were back. So that's an interesting thing. If you don't like, learning online, the whole e-learning experience, that's how it is, for the rest of this semester. We'll see how next year goes. But this is what it is at the moment. So we just have to, deal with it for now. You can hate it. You can hate, oh, I don't like writing papers online. Or just not online, but just, watching Zoom classes or watching videos. It's just, I don't need it. Or it's not how I learn. I need the actual, one-on-one, help. Well, this is how it is right now. So change is hard. We just have to deal with it. It's unfortunate. That's how it is. So for the penultimate lesson, we are looking at an actual lab that we normally would do, obviously in class. It's actually one of my favorite experiments. It's working with reaction rates. And if you've seen my YouTube channel, you've seen parts of the experimentation process, because it was posted for my honors classes earlier, because they did the lab a month ago. A similar lab, not the exact same, but a similar lab setup. So what you're doing today is watching 2 videos after this one, I guess, on a reaction rates lab. It looks like this. This is at least one of the videos. One of them says concentration, the other one says temperature. So you'll be looking at both of them today, and pretty much you're looking at how a reaction works and how concentration and temperature affect the rate and how quickly a reaction takes place. Now for this reaction, it's fairly complicated. With the actual document itself, there are 2 solutions that I primarily mix together, and it's fairly complicated. And what I do is I'm using 2 different little wells, and you're gonna see that in the video. So I'm not using pipettes, I'm not using beakers and mixing things to make a reaction. I'm using these tiny little well strips. And you're gonna see me in the video actually boom, 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 smack them together to make sure they react and they mix. And what I'm doing is I'm doing 8 different trials. If you can check this still frame, there's 1, 2, 3, 4, 5, 6, 7, 8. There's 8 different trials, or 8 different reactions going on simultaneously. And what you'll be doing is you'll be timing how quick the first 4 reactions take place. That's it, just the first 4. So it's kind of like in track, if you have 8 runners for a 100-meter dash, you only care about the first 4 that finish the race. Last 4, forget about it. They don't get any medal, ribbon, nothing. So the first 4 is what you care about. So what I'm going to do is actually go through experiment number 2 with you, because I like doing one example with you just to show you what times you could write down for your times in your data table. Because some people, again, get confused, so I just want to nip that immediately, I guess. Just to give you an idea, also there is some rates vocab. It's very quick and painless. It's about 7, 8 terms, maybe even fewer than that. But for the reaction, or for the lab, one of the wells has solution A and some water in it, and the other well has solution B and some starch. Now these are what the solutions actually are, if you check this out down here. And from biology, if you remember, starch, potatoes have a bunch of starch in them. Maybe in bio you remembered this. If you put iodine in starch, what color does it turn? Oh, it turns like a dark blue, dark brown, purpley color. It turns really dark. And so in this reaction, what's happening is that the solution A, this potassium iodate stuff, and this solution B, the sodium metabisulfite, more than you need to know, what they're doing is they're trying to create iodine. But what's cool is that the two solutions react to make iodine immediately, but right when the iodine is created, it actually reacts with one of the other solutions and it goes back to creating the product, these reactants. But then the reactants create the product, and the products make something else, and the reactants form more product, and the product makes something else. And so the iodine only comes out when one of these solutions gets totally used and it can't react with the created iodine anymore. So what happens is the iodine gets created and the starch in there says, hey, here's some pure iodine. It's going to turn this dark color. So you're going to see that in this reaction video. Okay. It's kind of cool. Again, it's one of my favorite labs we actually do. So I didn't want you to miss out on it. So that's why I made the video. So then there's all these videos right here. If you click here, you'll see the video data. So what I'm going to do with you is experiment number 2 for the concentration experiment, concentration data. So I'm not doing experiment 1. You can do it yourself. That's before, obviously, experiment 2. So in well strip number 1, now again, this part here would be for you if you were in the lab. So you don't have to worry about this. All you're seeing is that there's less solution A in each experiment as we go, and more water. So pretty much you're diluting solution A. So the concentration of solution A is getting less and less every single time. It's still going to react, but you'll see how the reaction changes. So what I'm going to do is help you with the data you would see for experiment number 2 and what you would need to write down. Now again, all the times are your preference, what you prefer to write down with your times, but I'm just going to show you what we're going to have to write down. So note for all the reactions, I have a little timer here. Hooray. So we have 8 runners. And all you're doing is you're recording the time it takes for the entire well to turn this brown-black color. So it's really cool. It comes out of nowhere. And so, bam, I got one time. So what I would do is pause it when maybe one of them is done. And I got 23.52 seconds for one of the reactions. So 23.52. I'm going to write 23.52 seconds. That's the first reaction. Now don't restart the video and do it again. That's finisher number 1. It's up to you. We're just looking at we're trying to get rough data. Okay, I'm trying to get an average. So I keep going. I'm going to look for the next one that finishes. I don't know, maybe it's hard to pinpoint the exact time that one of them gets completely covered, but I can use maybe 27.6 for 2 of them, maybe like this third one, maybe this last one. So 27.6 seconds could be this next one. 27.60 seconds, 27.60 seconds, And then last one, I don't know. There's a little under here that's not totally done. One of them looks done, 29.32, whatever. 29.32. You were looking for eventually an average, right? Then if you average these 4, you will get the average reaction time for experiment number 2. Okay. Now what you're noticing is that they're not all turning at the same time, which is actually normal. I like to relate this to popcorn popping. All right, so imagine you were doing a lab in which you had to time it took for every popcorn kernel to pop. You wouldn't get the same time for all of them. Can you imagine that? If all of a sudden they all popped at once, like mass hysteria, that's almost never going to happen. The chances of it happening are extremely low, almost zero, pretty much 0%. So this is kind of like that, where it depended on how big the drops were that I did that in, how well they mixed. Maybe a little bit of the solution fell out of wells when I mixed them, who knows. But that's what we're looking for. So that's experiment 2. You can use your own numbers, that's fine. You can use mine, it's fine. That's all we're looking for. And so eventually at the end, you're going to compare all the averages and just make a conclusion on how, for the concentration table, how the time or the rate of the reaction is changed based on the concentration of a solution. And the next video is temperature, and then I also gave you some catalyst data down here. So that's pretty much it for day 9. Again, make sure we get that vocab. And there are some questions in the lab at the way end with just why you think these things are happening. Okay, again, email me, let me know if you have some questions on stuff. Great.